All right, so as I start evaluating k's, so we'll start with k equals 1. And again, this is an infinite series, so we're kind of just doing enough of this that we clearly recognize there's some sort of pattern. So we might need to do 4 or 5 terms before we finally go, oh, okay, I can see what's happening here. So anywho, at k equals 1, that actually tells us C3, which is C0 over 3 times 2. And then when k equals 2, we're getting the fourth term, which is the first term over 4 times 3. And kind of already we can kind of see that, oh, okay, there's a pattern going on in the denominators, so that's nice. Then we get our third term, which is C sub 5, which is C sub 2 over 5 times 4. But remember, we had that observation that C sub 2 is actually equal to 0. So that means our fifth term in the pattern is 0, just like our second term in the pattern is 0. All right, so when k equals 4, we get the sixth term, which is the third term, so C sub 3, over 6 times 5. But again, we already have an expression for the third term. The third term was C sub 0, so C naught, 3 times 2. So this then gives us a C naught of 6 times 5 times 3 times 2. So I'm going to do a time jump and fill out several more of these, and feel free to join me on that. So if you want to pause and just fill them out, I don't necessarily think you need to see me plug a bunch of numbers in and simplify, but I'm going to put the chart on the screen here in a second. Okay, so as promised, I want to do a quick time jump so you can kind of see which terms there are. So of note, you can see that certain terms disappear on us. So the second term, the fifth term, the eighth term, which also corresponds with the 11th term, all equal 0. So we've got certain things in the pattern that equal 0. And then, well, what can we do with this? Well, based upon the fact that the original power series was going to look something like y equals, and then in terms of the general terms, it'd be C naught plus C1x plus C2x squared plus C3x cubed plus dot dot dot, right? And then we can go back in and we can collect up all these values of coefficients. So collecting them up, we recognize, oh wait, there's a pattern for C naught and a pattern for C1. So maybe we can try to collect those up. And then also identify that in general, our solutions are going to look like y equals C naught y1 of x plus C1 y2 of x. And then if we just group up all those different patterns, so the C naught pattern looks like it's connected to 1 plus, let's see, 1 over 2 times 3x cubed plus 1 over 2 times 3 times 5 times 6 x to the 6th plus dot dot dot, which really we can combine into a singular summation pattern here. So, let's see, 1 over 2 times 3 dot dot dot, and in general it's 3k minus 1 times 3k x to the 3k, and then our other solution, which again are all focused around the C1s. So the C1s, we would have an x plus 1 over 3 times 4 x to the 4th plus 1 over 3 times 4 times 6 times 7 x to the 7th plus dot dot dot, and then we can try to simplify that. K equals 1 to infinity of 1 over, let's see, 3 times 4 dot dot dot, that would be 3k times 3k plus 1 x to the 3k plus 1. I always find this interesting when certain patterns in math have a name given to them. So this is this specific solution, the specific pattern is referred to as Airy's equation, A-I-R-Y-S, Airy's, and it's a pattern that's actually important if you're going to continue in physics, specifically anything dealing with light and radio waves, aerodynamics. Those types of things. So, I don't know. The name itself, not relevant for our course, just the idea of how to solve a particular problem in this format.